Do you know the Schwarzschild radius of human Earth, Sun, and Milky Way galaxy? It will blow your mind. But before that, let's understand what is Schwarzschild radius. Ever wondered what happens when an object gets compressed beyond a certain limit? Well, we're about to dive into the fascinating concept of the Schwarzschild radius. This is the radius of a sphere that, if all the mass of an object is compressed within, the escape speed from the surface of the sphere would equal the speed of light. Imagine the sphere as a boundary line, a point of no return, beyond which everything, even light, gets trapped. Now, where does this term come from? It was named after the brilliant German astronomer Karl Schwarzschild. In the early 20th century, specifically in 1916, Schwarzschild provided an exact solution for Albert Einstein's theory of general relativity. And part of that solution was this concept, the Schwarzschild radius. This radius is associated with every quantity of mass. It's a key player in our understanding of extreme cosmic phenomena, especially black holes. You see, a black hole is an example of an object smaller than its Schwarzschild radius. Once a stellar remnant, or what's left over after a star has exhausted its nuclear fuel, collapses below this radius, it becomes a black hole. In a nutshell, the Schwarzschild radius can be defined as the radius up to which an object has to be compressed for it to become a black hole. In other words, it's the size an object needs to be squeezed down to in order for its escape velocity to be the speed of light. Let's put like this: you are in a car, and if want to escape, car needs to travel faster than light. So when you hear someone mention the Schwarzschild radius, you can now picture this invisible boundary line, this cosmic point of no return. And remember, when a stellar remnant collapses below its Schwarzschild radius, it transforms into a black hole, a region of space where gravity is so strong not even light can escape its grasp. But how does this concept relate to the enigmatic black holes in our universe? Well, let's dive right into the heart of darkness. But wait, there's more. This boundary is also known as the event horizon. You can think of it as the edge of the black hole, the last point where light or any form of radiation can escape. Once something crosses this horizon, be it a star, a planet, or even a stray photon, it's trapped forever. Now imagine you're an intrepid explorer, journeying towards a black hole. As you approach the event horizon, you would see the universe behind you contract, while the black hole ahead expands. The moment you cross the event horizon, the black hole would fill your entire field of vision. But don't worry, you wouldn't actually see anything because no light can escape the black hole. The event horizon is what makes black holes, well, black. The intense gravitational pull within this boundary is so strong that not even light, which travels at a whopping 186,000 miles per second, can escape. That's why black holes are invisible to the naked eye. Thus, the Schwarzschild radius is essentially the size limit for the event horizon of a black hole. Schwarzschild radius in the real world. Let's bring this concept down to Earth quite literally. Imagine you, a human being, your mass, your density, everything that makes you, you. Now imagine compressing all of that into a space smaller than the nucleus of an atom. That's right, an area incredibly smaller than the nucleus of an atom. This is the Schwarzschild radius for a human. Compressing a human to this extreme extent is, of course, purely hypothetical and not physically possible. But theoretically, if this were to occur, the result would be a black hole. Now let's consider our home planet, Earth. It's a massive entity with a diameter of approximately 12,742 kilometers. However, to understand its Schwarzschild radius, we would have to imagine compressing it to a size of just about 0.88 centimeters, roughly the size of a pea or a marble. Think about that for a moment. Our entire planet squished into the size of a tiny vegetable. The result? You guessed it. Another black hole. Moving on to a larger scale, let's consider our sun. With a diameter of about 1,392,000 kilometers, it's substantially larger than our planet. However, its Schwarzschild radius is just about 2.9 kilometers. That's less than the distance many of us travel to work or school every day. If our sun were to be compressed to this size, it too would become a black hole. The Schwarzschild radius gives us a fascinating perspective on the universe and the objects within it. It allows us to understand the immense densities and gravitational forces at play in the formation of black holes. So if these objects were compressed to these sizes, they would become black holes. What about larger celestial bodies? Let's dive into the cosmic depths to explore the Schwarzschild radius of some of the largest known entities in our universe. Let's begin with Phoenix A, the largest known black hole, with a Schwarzschild radius of 1,975 astronomical units. It's a cosmic monster. To put that into perspective, 1 astronomical unit is the average distance from the Earth to the Sun. That's about 93 million miles. Now let's move on to our home, the Milky Way. Our galaxy, with its dazzling array of stars, planets, and cosmic dust, has a Schwarzschild radius of about 1/4 of a light year. A light year is the distance light travels in a year, roughly 6 trillion miles. So the Schwarzschild radius not only helps us understand black holes, but it also provides a fascinating insight into the scale of our universe.